Bismillahirrahmanirrahim. In our interactive session, we had some questions regarding brittle failure, and although we discussed those questions, I thought about three of them could be of general interest. So I'm just going to take a few minutes to summarize those here. The first question regarded the energy released as the crack progressed, and we had discussed that that was a quadratic function of the increase of crack length. Now, I hadn't gone into detail deliberately here, but since people have asked the question, I'm just going to go into some detail here. To answer this question, the first question, I'll just repeat the question once again. Why is the energy released a quadratic function of crack length or increase in crack length? For this, we have to recall the situation. This is a crack, and if I magnify this part of the crack here, let's call it crack of length A. This is our convention. We take half crack length for central crack, and this delta A is the potential increase in crack. Whether it happens or not will depend on the energy balance. Now recall the stress trajectories we talked about. So as things stand, a lot of stress trajectories are passing through this point. This is a highly stressed region. Now imagine the crack extends. If the crack extends, there'll be empty space here, so no stress can pass like this. So now the stress trajectories will now pass through this region. Now this part and this region, they were highly stressed regions because of stresses and strains here. So a lot of strain energy was stored here. But now, if the crack extends, that stored energy cannot be stored anymore. So it has to be released. Now, what is the shape of this area that releases the strain energy? If this is the delta A, then roughly speaking, not being very accurate here, this triangle, or some people say this shape, this is the region that disposes of its energy stored inside it. So in other words, the stress trajectories now have to pass like this. So if this is delta A, this is also delta A. So how much energy is released? Obviously, it will be a function of how much stress and strains are there. Obviously, that will depend on different situations. But one thing is for sure, it will be a function of delta A square, because this is the area that was highly stressed, but now it cannot be stressed anymore, so it releases its energy. Obviously, there will be a similar area on this side also. So that is why this curve is a quadratic function of the crack length, or an increase in crack. The second question dealt with, if the first question dealt with this curve, the second question, although not in so many words, but it basically pertained to this line. And it was a question of the difference between brittle materials and tough materials. So what is the difference between them? I'll again take this. There's no doubt that a linear curve represents the energy needed for a crack to extend. But this line can be like this. For brittle materials, it is like this. And for tougher materials, this line is like this. Now, why is for one material the line has a low slope and for another the line has a much higher slope? That basically is because of low work of fracture of that material, and in this case high work of fracture. Now work of fracture is what makes a material tough. So I'll come back to work of fracture, but for now the energy released is a quadratic function, the quadratic function here. Similarly, this one we just talked about. Now if we superimpose both of them to get the energy balance, here this is the part where you get, this is the critical crack length. Please follow the last lecture. If you have if this passes by you or momentarily escapes you, go back to your original lesson and you'll recall. For this, if we superimpose the two, then you get this critical crack length. Obviously a very much bigger critical crack length than the crack length for a brittle material, and that is why we don't use brittle materials for engineering applications. So of course this subject deals with tough materials, but obviously the tough materials, so-called tough materials, also have a potential to fail in a brittle manner. That is why we are studying this. Now, what makes a material have a lower work of fracture and another material to have a higher work of fracture? For this again we'll have to see the crack tip where the crack extends. Let's say this is the extension of the crack. This was the original crack. Now, for a brittle material, there is no mechanism for work of fracture. That is, the energy cannot be dissipated in any mechanism. So what happens is basically, in a very simple way, uh, if you have enough energy to create two new surfaces and somewhat extra energy to disturb a few layers of atoms underneath, that's all you need to create two new surfaces. So hence a lower work of fracture, a lower slope here. On the other hand, for a ductile material, there can, for ductile materials, or we should more technically say for tough materials, there is some mechanism for work of fracture, and that mechanism can be different for different materials. For example, when we talk about timber, it may be something like interfaces, or and similarly for all composites, interfaces are one of the mechanism by which the materials become tough, energy dissipating mechanism. For polymers, for example, it may have something to do with the way their molecular chains are folded. So different materials have different mechanisms for toughness. For metals and metallic alloys, structural metals that we usually use in engineering, structural metals and their alloys, the mechanism for toughness is basically, it has everything to do with ductility of the material and ductility, and the mechanism for that is dislocations. Thousands, millions of dislocations move around, and when you have to extend a crack by delta A again, you obviously you have to create two new surfaces, but thousands of layers here get disturbed because a lot of plastic deformation happens here. So a lot of work goes in before you can, so this line, this energy needed line, this has to be very steep for brittle materials, this line is very, it has a very low slope. So this is what distinguishes a tough material from a brittle material. And we'll be focusing on ductility and these materials, but all other material, all tough materials have some sort of mechanism that ensures that a lot of energy goes into the system before a crack propagates or ultimately breaks into two. Now, the third question probably was the most pertinent of all, and which directly leads to our next topic. The third question was, again referring to our figure, if we know so much about the critical crack length for a certain stress level, obviously all cracks start their life as a baby. They start from scratch and then they grow. So all materials, we are not going to use a material with a crack bigger than the critical crack length, obviously, because it will fail immediately. So if all cracks start as very small cracks and then they grow, then how come anything ever breaks? No, nothing should break, because the cracks, all cracks will be smaller than the critical crack length, and because the energy balance is not there in their favor, they shouldn't grow at all. So we should be safe as long as we have made sure that the crack lengths are smaller than the critical crack length. One wishes life was as simple. The answer to this question is the F word in engineering, and that is fatigue. If there was no fatigue in this life, then it would have been very easy to design. Make sure it doesn't yield, and make sure the critical crack length is smaller. The crack length, any crack length present in the material is smaller than the critical crack length. That would have been all. But now there is something called progressive damage, and fatigue is probably the most predominant mode of that, in which a crack grows little by little with every cycle, and until it reaches the critical crack length, and then it breaks uncontrollably. But that is our topic for the next class, so I'll just leave it here. Thank you.